Hi there. Is this better? Who here says they can hear me? Okay, sorry about that. That's one reason I need to see people's. Oh, okay. So I guess you guys didn't hear my speech at the beginning, so I can't blame you for that. Um, Again, this is CSE 373. It's the lecture four. We will be talking about elementary data structures for now, little today, but I want to talk quickly. Any questions? First of all, about the logistical aspects of the course. You should be turning in daily problems. You should be starting to think a little bit about the homework one, because now we've with the big O stuff, we've covered enough that you start to be able to do some of the problems. And I encourage that. Um, I encourage people to come to the, what you call it. Again, I had people for the first time stop by my office hours on video, and that I encourage. Um, I will caution you that I will get on the office hours. Sometimes my class before this runs a bit early, so if you get on there before me, I want you to hang around. And of course, all the TAs, undergrad and grad, have office hours, so there's plenty of potential help. Okay, there's a question, I guess, about the what you call it. There are a couple of questions on the screen, although I like the questions orally. One question is saying, oh, on the homework, there's estimation problems. How many, pumpkin seeds fit in a bathtub or something like this. And the reason I guess I put them on there is on the assignment is one, these are kind of classic interview questions that give you an idea about how do you kind of reason about roughly what a quantity is. And if you think about it, the big O notation and the way we talk about analyzing algorithms is about roughly trying to quantify things, to get an order of, to get an idea of what is happening. So I want you to, for the estimation problems, make the best stabs that you can. Typically, these things work out that you make certain assumptions about the world. Like if I was going to deal how many pumpkin seeds fit in a bathtub, I would probably want to know how big is a pumpkin seed. And I'd want to know something about how big is a bathtub. And I can estimate, I think, in my head pretty easily now how big a bathtub is. I figure what's a bathtub? It's 10 by 2 by 2. That's probably feet, 10 feet by 2 feet by 2 feet. That's a bathtub. How big is a pumpkin seed? I don't know, but I guess pumpkins have pumpkin seeds. And I know how big a pumpkin is. And so how many pumpkins fit into a bathtub? I don't know. If I think about a pumpkin's maybe 1 by 1 by 1. That tells me how many pumpkins fit in a bathtub. How many pumpkin seeds would fit into a pumpkin? Now, that's something I'd have to think a little bit about, but this is the kind of reasoning I want you to try to do. Okay, and I think that it's very useful to try to figure that thing out. And that's why I have you do those things. And if you do a rough guess, you're going to come, a reasonable calculation. You won't all get the same answer. That would be wrong, but you're going to get reasonable answers, and that's interesting. Okay, so there's all kinds of things here about there's the big about the big O and the big omega and stuff like that. There's the big theta imply big O. Well, big theta, a function is theta of g of n. If it is big O of g of n and big omega of g of n. So certainly it implies both of them, okay? And the small o implied big O, okay? Small o, remember, which we'll talk about a little bit, was supposed to refer to something that grows strictly slower than. So if I talk about something that is, let's say I want something that is little o of n, that means something that grows strictly slower than n. Log of n grows slower than n. Square root of n grows slower than n. Okay, so in this case, the little o implies the big O. Okay, and the theta does not imply the big O because the theta is a tight bound, and little o of n is something that's dominance-wise less than that. Maybe that'll be clear when we go and do the daily problem. Any other questions before I get started on this? Okay. Actually, can you guys, are you guys capable of speaking? Somebody say something that's capable of speaking. I like to know that there's people out there.
Hello.
Bingo.
Hello.
Good. Great. Okay, we don't want to overdo that,
Hi,
but
Professor.
okay, I do want to hear questions. I do like seeing faces, and I suddenly I'm seeing I don't see as many faces on the screen as I'd like. If you're willing to show me your video, go ahead. Assuming it's decent and you'll show everybody the video. That's not what I'm asking about. But any questions about that? Okay. So what I'd like to now do is, let's hope that I can get this back here. Boom. Talk about the problem of the day. Problem of the day is one of these big O problems, and it is asking, find two functions, f and g, that satisfy the following relationship. Okay? And if f and g, if they don't exist, say you can't do it. Okay? So to me, this is very complicated without a picture. But so I'm going to want to try to draw pictures to see if my reasoning is, and then I can kind of understand it, I think. Okay? So what does this say? What is the picture telling me? The first picture is telling me f of 1 is little o of g of n. What does that mean? If I was drawing a picture here, that would mean that g of n is there. F of n has got to be much less than that, right? There's nothing close to that. Okay, so these are functions g of n and f of n. Maybe this is n, and this is log n. Is it possible that that is true, and f of n is not theta of g of n? Well, yeah, in this particular picture, they're not theta n of g of n. Does everybody kind of see that? F of n is growing strictly slower than g of n. Okay, it's in a lower dominance class. And if it's in a lower dominance class, it's not in the same dominance class. So this can certainly be held true, and I would probably vote for f of n being equal to, if I said f of n was equal to log n, and g of n was equal to n, I feel good about that. Any question about that? Do people believe this and agree with it? Okay. Not seeing much twitching here. Okay. Okay, good.
If we use the n square instead of n is the same thing, right?
Right. Okay. You don't like my n? Okay. I'll change it to an n squared. Does that change anything?
No.
No. Okay. So that's a perfectly fine thing to say. Okay. Log n is little o of n squared, right? You don't like my log n? Well, let me change it now. What if I made it n to the point 1.99? Does everybody agree that everything's still going to be just fine?
Yeah.
Okay, so this is good. Okay, let's look at the second problem. Is it possible that f of n is theta of g of n? Again, I got to draw a picture of that because this is always complicated. F of n and g of n are exactly the same thing. And, okay, the same thing as far as dominance class goes. And f of n grows slowly, much slower than g of n. Is that possible? F of n would have to be in two different places, right? It would have to be, so this can't be done, no way. Does everybody see what that reasoning is? There's a contradiction there. F of n equals omega of n includes that f of n is big O of it. And, you know, actually, I guess the contradiction here is that f of n equals theta of g of n means f of n is omega of g of n. Okay, so it can't get low. Okay, any questions about that? What about the third one? Is it possible for f of n to be theta of g of n, and yet f of n not be big O of g of n? And the
Yeah.
answer should be no, okay? Because f of n means that it's both big O of n and little o of n, right? I mean, no, f of n equals theta of g of n means that f of n is big O of g of n and big omega of g of n. So this is no, can't do it, right?
Can you draw the picture for this one?
Can I draw the picture of this one? I am going to draw my picture, and I'm going to think of my picture as these two f and g are so entwined. F of n, g of n, so close you can't tell them apart. Okay? And yet f of n is not big O of g of n. Where would f of n have to be relative to g of n if f of n was not big O of g of n? Seems to me you have f of n going out there, right? If f of n is not big O of g of n, f of n has to be something that is much bigger, right? Big O of g of n meant that f was less than or equal to g of n. If it's not less than or equal to g of n, it may be up there in outer space, but that can't be because we know that f of n and g of n are theta related. They're the same thing. Any question? That's why I got an X there. And what about the last one? Let me draw the final picture. Okay. Vroom, vroom. What do I see? I see that f of m grows at least as fast as g of n, right? So that's telling me that if this is g of n, f of n can sail above it. Okay? Is it possible that f of n is not g of n? Well, if it's O of g of n, well, certainly if f of n is sailing above it, okay, there's no reason why this can't happen. What if I say f of n is equal to n squared and g of n is equal to n? Is it true that that g of n is n squared? Does n squared grow at least as fast as n? I will say yes, so that part's true now. And is it true that n squared is not in big O of n? That's also true, right? So these functions exhibit it, and there is a way to make that true. Any questions?
I have a question on the second one. How about 2 to the nth? F of n equals to 2 to the nth.
Okay, so now you want me to say what is going to happen if I have f of n equals 2 to the n, and what is g of
2
n?
to the n plus 1 and 2 to the n.
2 to the n plus 1 versus f of n, g of n is 2 to the n.
Yeah.
Okay. Well, the first question is, are these two in a theta relationship? Okay. The answer is yes. 2 to the n is what you call it. 2 to the n plus 1 is only 2 for all values of n. 2 to the n plus 1 is only twice that of 2 to the n, right? So 2 times 2 to the n is an upper bound, and 1/2 of 2 to the n plus 1 is a lower bound. These two are within a multiplicative factor of 2 of each other. It is clear that for these two functions, f of n is equal to theta of g of n. Any questions about that? Does everybody kind of see that although they look different, the difference between 2 to the n and 2 to the n plus 1 is always just a multiplicative factor of 2 or a half, depending upon which is which, right? So they are the same big theta wise. But what does the omega relationship say? We say that f of n grows strictly slower than g of n if the limit of f of n over g of n, as n goes to infinity, goes to 0. What is the limit of 2 to the n over 2 to the n plus 1? What is the limit of that? As n gets
1
larger,
over 2.
what?
1 over 2.
1 over 2. Is 1 over 2 0?
No.
No, so that's not the little o means grow strictly slower than. Okay? So you worry about this sometimes when you think you've got a pretty good, exact analysis. Okay? Exact in the constant of the first term. Okay? And then you want to add a bunch of things that are smaller than it. You can describe that as little o of the first term. Okay? So suppose, I guess, if I wanted to show an example a little bit, just why I care about little o. What if I say that f of n is equal to 2n plus little o of n? Okay? What does that mean? Suppose I tell you that a quantity is like that. Could this mean 2n plus square root of n? That it could mean, right? Could it mean 2.01n? And the answer to that is no. Okay? So that's why we sometimes care about little o of n. If we're trying to describe, say, that the little garbage at the end, really, I know it can't be this big. Okay? Any questions? We may be giving this a little bit too much attention here, but do people understand where I got these answers from and why? Or any questions? Going once, going twice. Okay, sold. Okay, what I'd like to now do is shift gears. I'm now going to assume you guys understand what the big O notation means mathematically. And we're going to kind of use it, start using it. The reason we care is because when we come up with worst case analyses of algorithms, we want to find a simple description of the running time. And when we try to do worst case analysis of algorithms, you know, when we try to do algorithm design, one of the critical things is that we build our algorithms from well-defined data structures. Okay, you all should have lived through a CSE 214, which is our undergraduate data structures class. And, you know, one quote I once heard from a mathematician that I liked is that if you want to talk about human progress, you need to talk about it in terms of things you can do without thinking. And the canonical off-the-shelf data structures, things like stacks and queues, and we'll soon see binary search trees and priority queue heaps, things like that, are in some sense going to be algorithm components that we build bigger algorithms from. Because once we have an algorithm that realizes a certain set of operations with a certain set of time, we can then use it without thinking, okay, about worrying about the details in there. Okay, that's kind of the data abstraction, if you wish. Okay, and you know, a lot of algorithm design revolves around making sure you have the right data structure to represent what you're going to be working on. So there are two different kinds of aspects to data structures that we're going to worry about. One of which is the abstract representation. What are the operations it does? And then what is the implementation under the hood of how it does it? Okay, and this is like, this is the dirty details that will give us our running time. Any questions so far? So data abstraction is this idea that I suspect that they talked about in your earlier programming classes, about the idea that you can specify an object, if you wish, by the operations it supports, and hide the details of how it's actually implemented. So when we talk about a stack, okay, the abstract data type stack is a data structure that supports two primary operations. There is a push operation that inserts an item on a stack, and there is a pop operation that takes off the top item from the stack. Okay, and once we have a data structure or a data type that supports these things, we can use push and pop in our algorithms. Okay, and the question of how much time it takes for push and pop to run depends somewhat upon what implementation we have. The operations are defined by these abstract operations. The running time of the implementation as a function of the number of things in the data structure depend upon our implementation. For stacks, it's relatively, there are a couple ways you can implement them. You can implement them with arrays, or you can implement them with linked lists, unless you really botch it. Both insert, push, and pop should be able to be done in constant time per operation. But we'll see that other data structures are more complicated, in that there are many different implementations, realizing different time bounds for different operations, okay? And picking the right implementation for the right job is a critical part of algorithm design. Any questions? Boom. Okay, well, let's talk about implementing data structures. And when I think about data structures, the first breakthrough in my head, okay, is the difference between, I'll say, contiguous data structures and linked structures. In a contiguous data structure, you've got one giant slab of memory, and you are working in that giant slab of memory. An array is a giant slab of memory. A matrix is a giant slab of memory. Hash tables are implemented by giant slabs of memory. We'll talk a little bit about heaps, not today, but a couple classes from now, and they are going to be implemented. So certain things are, no pointers to connecting things. Those are contiguous data structures. Linked data structures consist of many individual chunks of memory, typically small, that are tied together by pointers. Okay. How many of you guys have programmed with pointers before? Okay, I assume, I'm kind of mentally assuming people have programmed with pointers. Oh yes, I'm seeing, oh yeah. Okay, so what are pointers? Pointers are things, we'll review this today. That's one of the reasons I'm going through this. But basically, linked lists are contiguous structures. Binary trees are contiguous structures. Graph adjacency lists, which we'll see, are all important linked data structures. And so my first division of how I see the world is something a linked data structure or a contiguous data structure? Any questions? Now, arrays are the mother of all contiguous data structures. And what an array is something that it's a way of storing fixed size data records. So all the elements of the array are equal size in the number of bytes. And you access them by an index, okay? So in some sense, if you're given the index of an element in an array, and you're given the size of each element in the array, the position of the location in memory of the 96th element in the array is the location of the first element, plus 96 times the size of the individual records. So in constant time, we can compute the memory location where the ith element should be in an array, which gives us constant time given the index. If we know the address of what we want to look up, we can pull it out in constant time. And this is one thing that makes arrays a great thing, because lookup is fast if you have the index. Another thing that's good about arrays is that it's all data. There was no pointers, no metadata. It's just a slab of elements. You can't get any more concise than slabs of elements. So that's efficient. It's also true that if we ignore the fact that we want to live in a RAM model of computation here, it is true that in modern computing systems, if you access memory successively by going from an element to the next element to the next element to the next element, modern memory systems do very well with that, because they kind of have these big caches and they load large chunks of memory in whenever they do an access. So arrays and cruising down elements successively can be a good thing, okay, in modern memory architectures. So you know, some arrays are good things. They're simple things. Simple things doesn't mean that they're bad things. Any questions? What's the biggest limitation of an array, though? When you declare arrays, what are the things that what is not good about an array?
You have to allocate the size before even like declaring the array.
Using an array, if I'm allocating a slab of memory, I have to make it big enough to hold my entire universe, okay? Because again, if I want to be able to insert something in the 756 millionth position, I have to have 7,656 million slots in my array. And I've got to get it all at once. So one problem with arrays is you fix the size, you know, in advance. And if you gradually need more and more things, if the enrollment of this class, I hope it's only going to be about 150. But if for some reason there's a sudden rush of people in here, I would be doomed if I allocated 200 slots and my class was as big as last year. Okay? So this gets into a variant of an array called a dynamic array. And I imagine some of you have programmed in languages where there are dynamic arrays. Have any of you guys ever used dynamic arrays that get bigger when you need them to get bigger?
Yeah.
Okay, I'm hearing array lists, I'm hearing all kinds of things. How is it that these magical arrays can get bigger when you want? Okay, and dynamic arrays work by starting out at a small size. Let's say something of size 1 or 2, something like that. Let's say something of size 1. And if we need, when we put something in it, we're happy. When we now want a second element, we don't have room for it. So let's double the size of the array, copy the new element, the old element, and put the new element in its position, right? This is fine through the third, until we do the third insertion. Why don't we now throw it out and allocate a bigger array, maybe twice as big? And now we have to recopy the X and the Y, and in goes the next element. Does everybody see how this scheme works? The moment we filled it, once the next request requires more than we have in the array, we double the size, copy things over, okay, and use this space until, you know, basically we run out. If we do this automatically, without, let's say, informing the programmer or requiring the programmer to take action, it provides the illusion the array is as big as we want. What is the downside of this scheme, though?
Have a lot of garbage data.
It's a lot of, there's a lot of, it seems like there's extra copying going on, and there's a lot of extra work going on. Okay? How much copying, though, is going on? Okay, let's try to analyze this scheme a little bit. First of all, I want to ask you, what's the maximum, if we're going to go up to n elements at the end, what's the number of copying of enlarging steps that are going to be done? We started with 1. We enlarge our array, we double our array every time we need to make it bigger. How many steps is that going to take? Well, how many times can we start at 1 and double it till we get to n? How much? This is one where people yell. What's the answer?
Log n.
Log n. Okay, by definition, what was log n? It's how many times do we double something till we get from 1 to n. So the first thing that's interesting here is the total number of enlarging steps is going to be log base 2 of n. Okay, and again, there was some concern. If I am not being sloppy, I usually will write the log base 2 of n as lg of n. Okay, but okay, does everybody agree that there's a total of log base 2 of n doublings to get to n? That's got to be clear. How much total work is done, though, filling this array till we have filled up n spots in it? Okay? It's obvious it's got to be at least n because we filled this thing in. But there is all this recopying that's going on, right? Does everybody see that? What's the cost of all that recopying that goes on in your dynamic array? Is that expensive or is that cheap? Okay.
Expensive.
Expensive. And again, that's what's the difference of expensive and cheap? Well, normally it depends upon how much money you got in your pocket, right? But that's not really the case here. Let's think about it though. If we fill an array of size n, a normal array of size n with n elements, how much work will we spend to fill it with n elements? 1, 2, 3. How much time? Order n. There's n slots. It took constant time to write in each slot. It's clear order n is a normal array. How much total work is done in this dynamic array? Well, there's going to be the final level where we did order n work copying it. Plus we're paying all the costs of these copying jobs. Right? We had to copy this element a total of how many times? How many times did x have to be copied? I will claim it had to be copied. How many times did this element x have to be copied? It was copied in the first, into the second, into the third. How many times?
N times.
How many times was the first element copied?
4.
Okay. Well, it's copied once per enlargement operation, right? How many enlargement operations are there?
Log n.
Log n.
Log n, that's right. So this element is being copied by n times, log n times. Is it copied more than any other element? I see some nodding yes.
Yes.
So the total work to copy it, you can argue, is going to be, there are a total of n elements. Each of them is only going to be copied at most log n times. N times log n, that gives us an order, n log n total work. Does everybody agree? Does that give us a theta n log n total work though? Maybe it actually is less total work than that. Okay? Does anybody see why, in fact, the actual copying, all the cost of all the copyings will be less than order n log n? Does anybody see why? How many of you are, well, okay, let me just think if this is going to work for now. What happens if I take the last step here was n, this step was n over 2, this step was n over 4, this step was n over 8. What happens if I sum up things that are basically 1/2 of each one of these things? Remember, each work that I'm doing, I did n operations on the last one. I did half as many before it, half as many before it, half as many before it. Does everybody see that if I took these halves and I put them over here, see that half? And see this half? And see this? Do you see that the total number, the sum of those halves is actually less than n to begin with? Okay. What is, okay, let's take a look at this thing. Again, we're going to take a look at it a little bit different. If we think of these total copying operations, okay, I am going to argue that the total copying operations, okay, are going to be basically order n, total. We agree in the worst case, one element is going to get copied n times. How many elements are going to be copied? Only no times. N over 2 of them are copied no times, right? All of these elements were never copied. Okay? These elements were copied once. These elements were copied twice. This element was copied 3 times. Okay? Do people see that we've got kind of a geometric series converging here? My claim is the total amount of work done is in fact going to be only twice n. Okay? Which means that the real analysis here is that this is going to be a theta of n operation. Okay? Any questions about this? Do you see the intuition how I folded these guys into getting a total of n?
I have a question. Is 2n is actually bigger than n log n?
Is 2n, that's 2 times n. Notice this is n, this is going to be n plus n. Okay?
No, it's fine.
So 2 times n is theta of n. It's not 2 to the n or something like that. That would be bad, right? Do people kind of see what has happened here? There is an interesting property of geometric series. Okay, the sum as I goes from, you know, even if I want to say 1 to infinity of 1 over 2 to the I. Okay, what does that come out to? That's 1/2 plus 1/4 plus 1/8 plus 1/16. Does anyone remember what this goes to? Okay, I hear infinite, and the answer is not infinite. The answer is incredibly finite. Okay? Actually, think about it this way, for those of you who are football fans. Okay? You are, here is the goal line. Here is an infraction. Okay? The one team shoots the other team's quarterback. That's a penalty, right? What happens when you get a penalty near the goal line? What happens? Those of you who are someone who's a football fan, what happens? Does anyone know?
Corner shot.
What?
You get a penalty.
Get a penalty. What's the penalty?
You can shoot from the corner.
No, that's
No, he's
not
talking
American
about
football.
American
That's some
football.
soccer thing. No one, this is America. We worry about American football. The ball goes halfway to the end zone, right? The penalty, if it's close enough, you move halfway to the end zone. What if the team brings in another backup quarterback and the other team shoots that one? That's going to get another penalty, right? What's going to happen with the ball? They move it halfway to the end zone, right? What if they keep moving it halfway to the end zone, halfway to the end zone, halfway to the end zone? After an infinite number of these steps, do they ever score? This is sort of Zeno's paradox, if you knew about such a thing. This is one where I'd really like to see some faces, because I don't know whether people are getting this or not. The answer is nobody scores. If you keep moving halfway to the goal line, you don't get closer there, over it, right? So
Get
the
close to
sum
zero.
of a half plus a quarter plus a eighth plus ... this thing gets close to 1, but never actually gets there. And that's why this dynamic array thing in reality, okay, is theta of n, not theta n log n. Any questions about that? How many people see it? Okay, I don't know if I'm allowed to get polls and yes or no's. What's happening? Okay. I don't know if I get to see what I get to see here. Okay, any questions about that? So the interesting thing is dynamic arrays are not bad because the total amount of work done is still linear, even though you didn't start with the original thing. Any questions? Okay, boom. Again, I give this kind of an idea, but one of the interesting things is that this idea of geometric series convergence, okay? We're not going to use this trick too many times in the class, but it's a very powerful idea that that when you have things that the sum of a geometric series is basically the size of the biggest value, okay? And that's kind of an important thing here. Any questions? Okay, good. Let me skip this one now, just because I'm a little behind, and that maybe throws us off a little bit. Okay, any questions about why arrays are a good thing and why dynamic arrays take theta of n work? If you didn't get that, I encourage you to think about it just as an example. That's one of the examples where a careful analysis can show you that the algorithm is better than you think it is. And it's because of the power of logs to make short work of things and geometric series convergence. Any questions? Good. Okay, if you don't have a contiguous data structure, you have a linked data structure. And one way to think about it is that, again, a pointer is a numerical value that represents the location, the address of a location in memory. I program in C for a variety of reasons, C language. One of the reasons is that it does give you, pointers that really mean something, and that they really are kind of close to the machine. In the programs that follow, we're going to assume that if P is a pointer, star P is what does it point to? If you have a variable X, and X is the address of X or the pointer to a variable X. And we're going to assume that there's a special null pointer, which is not used to mean a location in memory, but means that this isn't really a pointer and give up. Okay? Any questions about that? So what is a linked list? Let's just review that because that's a very fundamental data structure. A linked list is defined by nodes that have two fields in it. There is a data item, okay, which is what we got here, and a link field, okay? And so each one of the nodes in the linked list has two fields associated with it, okay? A data item and a linked item. If the data item is an integer, how much of the memory, what fraction of the memory in a linked list is representing data? Everybody kind of think about this. If you have each node as a data field and a pointer field, if your data item is an integer, how much of of your memory is actually storing data you care about in a linked list? About a half. Okay, does everybody kind of see that? If your objects get bigger and bigger, the overhead of the linked list goes down, I guess, fractionally. But it's no longer just pure data. How can we search through a linked list? Well, there are iterative algorithms and there are recursive algorithms. Okay, this thing is basically going to say that here, oops, got to go back, I'm in trouble here. Okay, we'll assume that there are two arguments here. One is a pointer to the linked list that, that we are interested in. And the other is the item X, that is the item we're looking for. So we want to search the list L for a particular item X. How do we do it? Well, if the list is null, L is null, meaning the pointer to the list says is null, that means the list has nothing on it. The list has nothing on it, then the item can't be found. We might as well return a null pointer. Otherwise, we're going to check, is the item pointed to by pointer L, the first item on the list? If it's equal to X, return L as a pointer to it. Otherwise, search the list that's pointed to from L.next. So if we go back to this example here, if we're looking for carp, if this is L originally, and we want to look at look for carp, okay, is Turing equal to carp? No, both great computer scientists. Then what are we going to do? We're going to change L to now point to L.next. That's going to make L point to here. And now we're going to resume searching recursively on a smaller list. That's what this procedure for searching is doing, right? If the list is not empty, does it match? Is the item of the head item equal to what we're looking for? If so, we found it. If not, let's resume our search on the remaining list. Any questions about this recursive procedure for finding the, doing a search? If I have a list of length n, what is the running time of this algorithm? Does anybody know? How much time will this search take on a linked list of length n?
O of n.
O of n. Okay, actually theta of n. Why would it be theta of n? Well, what if the item actually isn't there? Okay. And you'll have a list of all the presidents of the United States and you search for Skeena. Okay, you're not going to find him. Okay. So in that case, you would look at every one of the elements. That's why we say that it's really theta of n. But what would be the argument? The argument is, how much does this recursive call take? It does constant work checking if the pointer is null, constant work checking if the item is X, and then if it doesn't, it spends, basically after constant work, reduces it to something that is of size 1 less than that. You could say it has n elements and it spends a constant amount of time for each one of these elements. If you want to be a little bit fancier about it, and don't let this confuse you, if you don't like it, you don't have to. You could even write a recursive equation for it. that the running time to search for an item on n elements is constant plus the running amount of time it takes to do something for n minus 1 items, right? This is kind of a recursive equation to say the same thing, okay? But regardless of that, this is going to be theta of n. Any questions about that?
I had a question.
Yeah.
So, I mean, if you sort of look at like the equation that you just wrote, in that, if you sort of did like, I mean, I don't know if this is accurate, if you could sort of do that, but t of n minus 1, like you could sort of think that could you look at it as like that being a higher degree sort of element in your equation and sort of say that, oh, it's the running time is going to
No,
be
I don't
n
want to
because
think,
of that?
that's not what it is. Actually, what I want you to think about it, actually, if you've seen these things, this is a recursive equation, right? This was a recursive algorithm. It was an algorithm that called itself, right?
Yeah.
This is a recursive equation. It's an equation that calls itself. Okay? We will talk about recurrence relations later in the semester. Okay? How many of you have taken AMS 301 already? Some of you are, I'm picturing a computer scientist. You've probably taking it or have taken it. If so, if they do a good job, they will be talking about recurrence relations in there. We'll talk about it a little bit later. Don't panic, okay? But it's kind of, this is an instance of that kind of thing. And we'll see that later. Any question later in the semester? Any question?
Wait,
Okay.
Professor,
Yes.
I still don't think I understand why it's theta of n and not O of n.
Okay, my upper bound is I spend, what are we looking at? We want to know what is the, let's say that f of n is defined as the worst case running time on n elements, right? Now, that's what we want to reason about. This thing says, well, look, it's going to spend, if I give me a list of length n, it's going to take constant time. I'm going to look at each element. I'm going to spend constant time. There are at most n elements that I'm going to look at. The running time is therefore less than or equal to some constant times n. Okay? And therefore it is big O of n. Now, think back to the, the previous example, the dynamic arrays. Big O was an upper bound. Remember how I gave you a convincing n log n upper bound for how much work you would be doing? There's n things. Each one of them is being used at most log n time. Therefore, it took at most n log n time. That was the upper bound. Now, unless I show you a lower bound, an example that actually takes that time, maybe your analysis is too soft. That's what happened to me with the dynamic array one, right? The n log n analysis is an upper bound, but it's too soft. Suppose I go to you and say, insertion in a linked list takes order n cubed time. Let's say I go and tell you this, order n cubed. Searching a linked list takes order n cubed time. Am I lying to you? No, I'm saying something that is absolutely true. I'm saying something every bit as true as Skeena is worth less than $1 billion. You only get an interesting answer when your analysis is tight enough to be interesting, right? And the way that what you would really like to say is not that it's O of n cubed. You'd like to say that it's theta of n. That the worst case running time, in fact, is bounded by a constant upper and lower times n. Okay? And to do that, you need to do a upper bound analysis and mentally give me a bad example that realizes that. For searching in a linked list, what's the worst case in a linked list? Searching in a linked list, what's the worst case?
That is not there.
It's not there. If I'm not there, am I visiting all n elements?
Yes.
And am I going to spend a constant time with each element? Does
Yes.
that mean that this algorithm is going to spend at least n or at least omega n time? Yes. Okay. In fact, that you can get away with that, it's theta of n. The argument that there's an upper bound, which is usually what we need to make, okay, gives us a big O upper bound. We like it when, in fact, that is the right function and not a hideous over approximation. Okay, and the best way to prove that it isn't is to show me an example where that algorithm will in fact actually take that time. That's where the theta is. Any questions? Okay, good. Okay, how do we insert something into a linked list? Okay, and again, what is the cost of inserting something into a linked list? And again, let's just practice our pointers. Here we've got L, we've got a linked list. Okay, what do we want to do? If we want to insert a node X, okay, at the head of the linked list, how do we do it? Well, X here was an item type. It was a key. What do? We allocate a new chunk of memory. Oops. Copy X into this thing. Malloc is a way of copying, of allocating a chunk of memory. We're saying what P point, and P is what this is going to be, the new item. What P points to dot next, let's have it point to what L points to. Okay. And then basically change L to point to P. So we'll say that L points to P. Okay. So inserting something at the head of a list is not that hard. It's good for you to practice your pointer manipulation, just to make sure you really understand this stuff. I know people don't like programming with pointers until they get used to it. Okay, any questions? How much time does it take to insert an item into a linked list? If I have a linked list of length n, how much time does it take to insert an item in at the head of that?
Constant time.
Constant time. Does everybody see that it doesn't matter how long the list is, right? This would be done in theta of 1 time. Okay, any questions? Okay, good. How much time does it take to delete something from a linked list? And this actually is a little bit tricky. Okay, what am I going to want to do? Suppose first what I'm going to want to do is find, if I have a linked list, let's say I have a linked list L. And I want to delete this guy, what X points to, this guy. How do I delete, if I'm given L and I'm given X, how do I delete that particular node? Okay, what must I do? Okay, conceptually, what I've got to do is, let me try another color. What do I got to do? I want to be able to find which element points to L. Does everybody see that if I want to remove the item X points to it, I've got to find the element that is before it in the linked list. And then I can splice it out. Once I know an element before it, What are my pointer manipulations? I have to take the outer pointer from here and have it point to x dot next. If I copy this pointer and I replace it by x points to dot next, then this guy is out of the list. Any questions? But what's the cost of finding the element before me in a linked list? Suppose I give you a linked list of size n, and I give you a pointer to a particular element. How much time does it take to find the element that points to it? Okay. Okay, I'm seeing n. If it's a long list of length n, how do I find the element that points to x? Well, if all I have is my head of my list and x, I've got to go to the head and say, are you x? Are you x? Do you point to me? Do you point to me? Do you point to me? Yeah. That might involve searching through n different items, right? Each of which would take constant time. Notice that it could take as bad as theta n time to find the predecessor. So in a singly linked list, to delete a particular item I have the pointer to, it would then be theta of n. Any questions about that? You see why I have to find the predecessor? Do you see what the manipulation is? I've got to go find the item before me, okay? And then to splice it out, once I have the item before the one that I want to delete. If this is what I have marked for extinction, what do I want to say? Basically, if this is L is pointing to the predecessor, or pred is pointing to the predecessor, what do I want? Pred dot next is going to be equal to what x points to dot next. And then I want to free up the memory to eliminate that node cell, right? The act of copying of copying x dot next into pred dot x, that removed that pointer, that removed that value. I then have to remove this memory and free it up. Any questions? Okay, good. So what are the good things about linked lists? Why do people use linked data structures, and why do people use linked lists? Part of that is actually people don't use linked lists for quite the reason they think. Some people will say, why do you use linked lists? You'll say, save memory. Well, notice that half the memory in a linked list was wasted by pointers. So it isn't quite a matter of saving memory. It's a matter of using memory where you want to use it, okay? Linked lists give us flexibility about where we use our memory, okay? And that's what I think it is, okay? So the advantage of linked lists, you're flexible enough that memory overflow doesn't occur unless your memory is really full. And when you have large data objects, moving pointers to the objects is easier than moving the objects themselves. That's one other reason why linked items are good. Okay, any questions about that? Okay, good. Now, one of the ways to get rid of the problem that I just had with linked lists, the problem I had is that it was hard to find if I have an element in a singly linked list. It's hard to find who's pointing to me. Does everybody get that? If you have a doubly linked list, now each cell is going to be a data item, X, a next pointer, and a previous pointer. Okay? If you have a doubly linked list, you point to the item before me and the item after me. Okay? Which are more efficient, singly linked lists or doubly linked lists?
I think doubly linked list.
Doubly, I think it depends upon what you're trying to do. Okay. The cost, what is the cost with doubly linked lists?
Space.
You use now, instead of twice as much memory than your data fields, you might use 3 times as much memory as your data fields. Is that a problem? Well, in big O world, no. In real world where you're paying for memory sometimes, okay? What's the complexity of maintaining these pointers? Okay, well, actually, building a doubly linked list is not really any more expensive in a big thing in terms of running time. It's still going to be theta of n to add or delete an item, and it gives us the flexibility to figure out who's pointing to us. So if you need doubly linked lists for your algorithms, in a big O sense, it's harmless to use them. If you don't need the power of reaching back to you, don't use them, okay? Any questions about that? But if you need to, since we're thinking about things in terms of worst case running times, sometimes there's an advantage. I like to think of the difference between singly linked lists and doubly linked lists sort of a little bit like dancing. When you're at one of these parties where people form these chains and everybody puts their arms on the shoulder and starts bobbing and weaving with that. Remember that before the coronavirus set in? I don't know if you've ever been doing that kind of thing. That is a conga line, and that is a singly linked list. You know who you're grabbing ahead of you. You don't know who's got their hands on your shoulders from behind. Other dance things, you form like a world where you touch, baby, you form like a conga line, where or a dance kick line, okay? That actually is one way you have pointers to both sides. You have more flexibility, but there are costs to it. Any questions about doubly linked versus singly linked structures? Any questions? Okay. Now, what are the things that we're going to build from these linked data structures, linked or contiguous data structures? Well, there's certain abstractions that we care about. One is a class of containers called stacks and queues. What are stacks and queues? Stacks and queues support storing items and retrieving them based on the order they were received, not based on content. If you want to look in if you have a queue and you want to look up, is Joseph in the queue? You've got to look through all the elements. You don't get any insight there, okay? But if you are or relevant things. In a stack, you insert things in according to a last in, first out operation. You push things on the stack, they keep getting higher and higher, okay? A pop takes the last thing you inserted. In a queue, okay, your two operations are NQ and DQ. You're supporting first in, first out. Which kind of a data structure would you want to represent the line of people, let's say at lunch? When people go to the SAC for lunch, what do you want? You want them to observe a queue. Why is that? If not, the last guy to walk into the cafeteria gets served first, right? That doesn't sound very fair, okay? So that's why queues are used for supporting lines. In a lot of other situations, however, stacks more accurately model what you're doing. In your refrigerator, do you extract food in a first in, first out order or a last in, first out order? Okay. If you are worried about freshness, it should be first in, first out. If you're like me, you get hungry and you grab the first thing you see. What is the first thing that you see in the refrigerator? It's the last thing you inserted, right? And so in some sense, many things get modeled by stacks. The important thing is that both of these can be implemented as either stacks or arrays. Both of them can be implemented in constant, so that each operation of an NQ or a DQ or a push or a pop, okay, can happen in constant time. Okay, any questions about that? And so we will see when we get to graph traversal, the difference between queues and stacks turns out to be an amazingly important difference. Okay, but as data structures, both of them can be supported in constant time per operation. Which should you use if you have items that you don't care what order you process them in? Are you better off using a stack or a queue? Okay, big O-wise, it doesn't make any difference. You're accessing each object, getting each object in constant time. How can you do better than that, right? Any questions about that? Okay. And that's sort of my story about why stacks and queues are important. Any questions about stacks or queues? Okay, I trust you implemented such things in a data structures class or kind of, but again, maintaining them as a linked list, things become pretty easy to deal with. Okay, the last topic for today, but it's an important, basically it's just going to be an introduction to dictionaries. Dictionaries are one of the most important classes of data structures, okay? And dictionaries are data structures that support 6 different types of operations. And we're going to spend the next class talking about dictionaries, so you darn well better understand what these operations are. And so let's go carefully through what are the abstract operations supported by a dictionary. The first thing is search. And a search query is you're given a dictionary data structure S, and you are given a key. Notice the K is in red. That's important that that K is in red. You're given a key and a dictionary structure, and you want to return a pointer to the item in the dictionary, such that the key of that item is K. Okay? These are, again, I'm hearing, are these maps or these hash maps? First of all, some of these, the kind of data structures you guys deal with, hash maps and things like that, are dictionaries. So it's fair to say, are these maps? No. Are hash maps dictionaries? Yes. At least they support some of the operations. But let's see what all the operations we want on a dictionary. Search lets us look up a key. The second argument recognizes a key. Insert inserts a new record. We're inserting a record X into our data structure. Typically, a record is going to be a node. There's going to be some key field K and maybe some extra baggage. Suppose I am building a data structure to represent CSE 373 students and their, their grades. Well, the key is the grade. The extra baggage, the key is the name, excuse me. The key is the name. The extra baggage is the grade. So we're going to be inserting records, okay, with the property that we want to be able to look up items by key. If I have a data structure ordered by name, I can't look you up, say, is there someone in my class that has a GPA, a grade average of 93? That's not something I can do. Is there someone in my class named Harry Shapiro? That's something I can do, okay? So search is with keys, insert is with records. Delete says I am given a data structure and I am given a pointer to the item I want to delete, okay? So notice that here I'm assuming I have a pointer to what I want to delete in the dictionary. How do I get a pointer? Suppose I want to delete Skeena from the class. How do I get a pointer to where Skeena is in the data structure? What do I have to do? Okay, I call my search procedure. Again, I like it when people yell that out rather than type. Does everybody kind of see? To get a pointer for a key, I have to go and do the search. So I do a search, I have search, insert, and delete. I have two other sets of operations that I care about on dictionaries. One is to find the minimum and maximum element. This is going to be the element that's first in alphabetical order, if they were names. That's the min. And the max would be the one that's last in alphabetical order. Okay, if they were numbers, if my key was a number, min would be the smallest key in my data set, max is the biggest key. Does everybody see what these operations do? The input is a dictionary data structure, and I say, give me a pointer to the max. Give me a pointer to the min. Okay. The final operation is what we call predecessor and successor. And this means gives me the logical element that is logically before, right before what X points to, or right after what X points to, in sorted order. And this is the one that confuses everybody. Suppose I have a dictionary which has the items 1, 3, 2, 5, 5, and 4. What is the logical predecessor of item number 2? What is it? It is the element that is right before 2 in sorted order. Which one is that? 1. Does everybody see the predecessor of X is 1? What's the successor of X? It's going to be 3. Does everybody kind of get that? It does not mean the neighbor in the linked list. It means in the logical order. See that big red logical? Everyone's got to remember that. Any questions about that? A dictionary is a data structure that supports all of these operations. Search, insert, delete, min, max, predecessor, and successor. Any questions about that?
Could you explain a little more about the ordered set aspect of the predecessor and the successor?
Well, let's just stop to think about it. Let's look at an implementation. Suppose I am representing my dictionary as an unsorted array of elements. Okay, 2, 6, 7, 10. Suppose I want to know if I have an array of n elements, and I want to know whether it contains the item 17, the key 17. How do I do that? What do I have to do to tell if my array of n elements, if it's unsorted, contains the item 17? What do I have to do?
Search.
Search. How do I search it?
You would go through the whole,
Where I goes from 1 to n.
Yeah.
Is A sub I equal to K? If it is, stop, ding, ding, ding. I found it, it's in the ith spot, right? If not, keep going. What is the running time of that algorithm?
O of n.
O of n. Can it actually take n steps? Yeah, if the item it's looking for is at the end or isn't found, right? So the truth is that's an argument that it's theta of n, right? How do I insert an item into an array? What's the cost of it? Let's say I have an array and I have an upper bound. I know how many items are in my currently in use. To insert an item, the new item in there, I go to the ith plus first location, I bop I up by 1, and I then copy it into the ith location. How much time does it take to insert an item in the array? Constant time. How much time does it take to delete an item from the array? Okay. If I want to maintain a data, delete it, how much time does it take to delete an item from an unsorted array? Suppose I want to delete the Xth item. What could I do? How do I do that deletion? Somebody. How do I do it? Okay. Well, one possibility, the simplest way, the most efficient way, would be to just take the current ith item, the last item I have, copy that over into this location, overwrite it, and then decrement my counter so I have one less item in there. If I do it that way, delete can also be done in constant time. How do I find the biggest number in my array? How do I do that? How much time does that take?
O of n again.
O of n and theta of n. I have to go through all n elements. Okay? So min and max take n time. How much time? How would I find the predecessor of a particular item? How do I find the predecessor of item number 2? If X is in fact the item 2, what do I got to do? I've got to look at every element in my array. Are you before less than X than 2? If so, you're a candidate predecessor. Are you less than are you in fact greater than my current predecessor? Actually, let's say I wanted to find the predecessor of item 10. Is 3 less than 10? Yeah, that's interesting. Is 1 less than 10? Yeah. Is that interesting? No, because it's bigger than 3. Is 4 interesting? Yeah, that's my new predecessor. 5? Okay, 6, new predecessor. 7, new predecessor. And that's the last one, right? I claim in one sweep through the array, I can find the predecessor or the successor. That would take n time, correct? Okay, we're running low on time. Let me just do one last thing here. What if I use sorted arrays? How much time would these dictionary operations take on a sorted array? If the array was sorted, how much time does it take to look for an item? How do I do it? If I want to look in a sorted array, how do I do it? I'm not hearing it, but binary search. How much time should that take? Log n time, right? How much do I insert an item into an array if I'm doing binary, if I want to keep it sorted? Suppose my arrays contain the items 1, 2, 4, 5, 6, 7. I now want to insert a 3 in the array. How do I insert that item and keep it sorted? What do I have to do? I start on the left. Does it go between here? No. Does it go between here? Yes, it does. Once I find where it goes, what do I have to do? I have to make room for it. And then I can write this element in. So my claim is that in order I have to search, then move this stuff to make room for it. In fact, that could be theta n.
I have a question.
Yes.
What if the array is already full? Like you don't
The
have.
array is already full. Let's say I use a dynamic array. Let's just say when I'm assuming this, I'll assume my array is big enough. Okay. So I'm not going to worry about that. Okay. Delete. Similar thing. Once I know where it goes, I am going to have to move elements to fill up the hole. That's going to take theta n. If the array is sorted, but min and max suddenly become easier operations, right? The min is going to be the first item. The max is going to be the last item. So that can be fast now. Logical predecessors and successors are really just neighbors in this sorted array, right? And so, in fact, these operations become fast. So sorting speeds up some operations, makes other ones slower. Does everybody see that? Data structures have the property that how you implement it, some operations become faster, some become slower. Okay, I know I ran long. I'm going to cut this right now with one begging you. Next the next daily problem is the most important daily problem of the year. Okay, so be sure you think about the daily problem to make sure that you understand. If you can figure that one out, you'll understand a lot more about data structures and how they work and what the trade-offs are. So make sure you do that. Have a good weekend, and I will see you guys next week. Okay, thanks a lot.